So today I will be focusing on concrete batteries for architectural energy storage. I'll be talking about the most produced material on planet Earth, concrete, and it's most produced and used material on the Earth because, for a good reason, it's strong, durable, versatile, but most importantly, it's very inexpensive material, construction materials, material. And compared to other construction materials like wood, ceramics, glass, or composites or metals, it's an order of magnitude cheaper, which definitely makes a huge difference. And it's very difficult to populate this space of the Ashby plot on the left side, where materials cost 10 cents per kilogram. So that said, we do face an important challenge because of the extensive use of this material, and considering the projections of the UN that by 2050 we will have about 10 billion people on our planet. But most importantly, out of these 10 billion people, 6.7 billion will live in the cities. And that number translates into a need to build cities. And, to build our cities, we use standard materials, steel, concrete, and glass. And in order to build a housing home for that growing, exploding urban population, we will need to build an equivalent of 13,000 buildings every day starting from now. So that translates into a huge number, a huge amount of material needed. And when it comes to concrete and cement as a binding material, for each ton of cement produced, we emit a significant amount of CO2 into the atmosphere. It's about 0.89 tons of CO2 emitted for each ton of cement produced. And current production that is projected to increase is 4 billion metric tons per year, translates into significant CO2 emissions. Unfortunately for us, we currently have available solutions to mitigate about 50% of these emissions. And in order to reach carbon neutrality, which is should be our goal by 2050, we still need 50% solutions for 50% of these emissions. And in our labs, we like to think that the solution is multifunctional concrete. So concrete that is not only load-bearing material that is currently in use, but it's also self-healing and extending the lifespan of everything we build, or is carbon sink and mineralizing CO2 from thin air, or even conducts electricity. So that's what we believe is the future of concrete. And in our labs, we are developing these multifunctional solutions to actively create out of concrete that we use avoided emissions. And that you will learn quickly in this webinar are quite significant numbers, and it's a great opportunity for us to think about concrete as a part of a solution instead of a problem. So we are talking about, as I said, self-healing, CO2 mineralizing, energy storing in the foundation of your house, which I will outline a little bit today, or even melting the snow. We just got a blizzard here in Boston. So it would have been very nice to have a self-heating sidewalks in front of my house to get rid of all that snow, or even maybe have electric cars charged by roads that are that have energy storage beneath, made out of concrete. So I would like to focus a little bit, tell you a little bit about self-healing concept that is developed in my lab. I want to remind you that 2000 years ago, ancient Romans, lived an architectural revolution, true revolution, due to the discovery first, and the use of concrete. The discovery was the addition of volcanic ash into the lime-based mortars to then create concretes. And recently, we kind of were able to refine a little bit our understanding of how Romans made their walls. Here we are talking about a technique that is called hot mixing, where dry premixed volcanic ash and quicklime is saturated with water. And here's the video outlining a little bit the process of hot mixing, where you see the white chunks of quicklime and the pozzolan. Volcanic ash is, you see, saturated with water and mixed, and this mix heats up literally, and that's why it's called hot mixing. And it leads to creation of reservoirs of calcium that eventually produce, and Romans didn't know that this would lead to a self-healing concrete. But that's something that we looked into in my lab, and eventually came up with a Roman-inspired self-healing concrete that is able to extend the lifespan of concrete by 50%, by basically slowing down the ingress of water and elements and ions through cracks to reach the rebar and eventually corrode the rebar. So that self-healing, autogenous self-healing mechanism is able to close fractures up to 0.5 millimeters, making it true self-healing concrete. And by making some assumptions, for example, of extending the 50% lifespan to maybe 100 years of what we build, and avoiding two maintenance and repair schedules over the life cycle of this concrete, we reduce by 40% the CO2 emissions associated with the cement production. That compared to the standard concrete, that's really significant. Now, if we look at that general picture where we have 100% CO2 emissions associated with cement production, and we integrate available solutions of 50%, and now do introduce the functionality of self-healing into everything we build, we create 40% of avoided emissions, and that totals to minus 90% total saving on emissions. And that really brings us very close to have a carbon neutrality by just giving a self-healing characteristic. But let me now talk about electron-conducting concrete that really makes us very excited in the lab. And here we are talking about making concrete that is an insulator, a conductive material, meaning that we introduce some sort of a conductive material, and we focus on nanocarbon black that basically mixed with the cement and some admixtures and water, and of course aggregate for concrete, then turns into carbon black cement composite that conducts electricity. And the mechanisms behind this are through nanotechnology, where these nanocarbon black self-assembles during the hydration process into percolated volumetric wire. that is a physical chemistry-driven process and therefore highly repetitive. Recently, we kind of investigated closely the micro and nanostructure of this composite using different electron microscopy tools, including this FIB SCM tool that has a resolution of 10 nanometers, where our nanocarbon black generally is 40, 50 nanometers. And using this tool, we were able to really resolve all the distribution of different components, including solid hydration products, yellow in this 3D reconstruction, red is nanocarbon black, and pores. And I want to stress this pores structure because it's really typical for the cement carbon composite that the pore structure is connected, allowing the transport of ions, which will be very important for our cement batteries. But the most importantly, you see this mixing leads to a connected carbon network that is able to now basically have electrons jumping from one carbon black to another, making entire material, bulk material, conductive. So in these studies, we show that the 90+% of carbon in all the entire volume is connected, which is very important. Okay, now applications of these materials are incredible, important. Another Ashby plot here is a plot between resistivity and the cost of the final product, where EC cube, you see, is in the order of pure silicon conductivity, so conductive material, whereas the cost is not affected significantly because the amount of carbon black needed to make it conductive is very small. We are talking about the percolation threshold of about 2.5–3% to make it, to create this percolated nanowires. Good. Applications, as I said, are multiple. You can use it for, free throw resistance, and so increase the longevity. You can use the Joule effect to heat this material that basically material heats proportional to the voltage to power of 2, and it really, with few volts, you basically get the temperatures that approach 100 degrees C. Energy storage is another application, and also some high power electromagnetic shielding is possible. But let me focus on these two applications where we put significant work in. Self-heating is very simple. Here's a demo in a park in Japan, where we designed these self-heating sidewalks that basically do the job quite nicely. In Sapporo, they get a lot of snow, similarly to us here in Boston. And you see, last year we were able to nicely melt all the snow that was falling on these sidewalks by applying very small voltages. And here is an important number that comes from our Hessam's work, where Hessam calculated the avoided emissions compared to standard concrete sidewalks. Here are some details of these calculations, where he considered a conventional system where you need a maintenance, de-icing, salts, repair and replacement of the whole slab after every 15 years, and mixed design is conventional concrete, whereas this self-heating multifunctional system would not require salt and repair displacement slab every 20 years and energy consumption about 110 kilowatt hour per year. Mixed design is our carbon black, 10% carbon black in conventional concrete. And yeah, the results are that, life cycle greenhouse gas emissions are significantly lower, 24% lower compared to the conventional system. Very interesting results. Now, when it comes to energy storage, here we are talking about this dream of making the transition from non-renewable energy sources to renewable energy sources, and that dream is possible only with scalable energy storage solutions. And what we believe the scalable energy storage solutions might be based on EC cube. Supercapacitors. There are many reasons why we believe that that's the case. One important reason is that ingredients and necessary to build EC cube supercapacitors batteries is the fact that we don't need metals, so it's carbon and cement, ubiquitous materials on planet Earth. And most importantly, the durability of supercapacitors in terms of cycles is much bigger compared to batteries. We tested our systems to 100,000 cycles of charge-discharge, which outperforms significantly what batteries can do. Good. So when we talk about that dream, we envision literally architectural geometries and modular units that are embedded into new buildings. Basically, you have platforms, columns, walls, arches, vaults, domes, all somehow integrating energy storage capacity. And here is the unit cell that we designed in the lab, where you have two electrodes that are separated by a separator and then connected in series through current collectors into, for example, a column here. And actually, here we show also a possibility of making an arch that we literally built in our lab. Here is the picture of an arch that is charged and will lit this LED only when we put 6 kilograms of the weight on this arch, foreseeing, you see, some sort of sensing, autogenous sensing capacity of these structures. And of course, when it comes to energy storage, our prototypes evolved significantly from 1.5 cubic centimeters, 1 volt single unit to 12 volts, 18 centimeter cube prototype. Then you see 3,000 centimeter cubic 12 volts unit, and then the most recent unit is quarter of cubic meter, 25 volts prototype. And this evolution in size confirms an important outcome, a theoretical outcome, that these systems are scalable. Independently from the size, you continue to maintain the performance, which is very, very important. Let me focus on this 12 volts, 0.03 cubic meters, 3,000 centimeter cubic unit, where basically an important number is this energy density is 300 watt hours per cubic meter of energy stored, energy density. So that translates in the need of certain volume to satisfy, for example, daily need. I will discuss that later. But you see, this unit here can operate 12-volt little computer fan and 5-volt video game console, which is kind of cool. 25-volt prototype is a bigger, of course, system, but again, assembled in the very similar way with a separator and electrodes here. And then we have 50, because it's 25 volts, we have 50 electrodes, so 25 units. And then you basically end up with some sort of casing and system. That here is one in our lab, and it's so nice to have this big LED lit for hours in the lab, which is really encouraging, particularly when it comes to perhaps leveraging these technologies in the developing world, where access to light in the evenings is quite the challenge. We made several of these with our colleagues in Japan, in Fukushima. Here are the pictures, and now let's discuss where this can take us. I would like to discuss the case of future of housing. So you could imagine basically a house foundation made out of EC3. And if we consider daily requirements of about 10 kilowatt hour in average per day, that translates into, you see, 33 cubic meters of EC3 required with that 300 watt hours per cubic meter energy density. So that basically we actually improved significantly recently just by changing the electrolyte. So if you go away from water-based electrolytes, where the water splitting limits our performance to 1 volt, you remember that 1 volt is each unit cell, and it's 1 volt because of the water potential water splitting at the 1.3 volts. So we always keep that voltage low. But here, just by extending the voltage through other electrolytes different from water, we hit 2000 watt hour per cubic meter, which then translates in only 5 cubic meters of EC3 required in the foundation to satisfy 10 kilowatt hour daily need. And so imagine now this house that basically collects solar energy during the day through the panels on the roof and channels it to our supercapacitor foundation at the bottom. And then when the sun is gone, you start using that energy stored in the foundation for your needs in the evening. That basically, I will finish here and then move on. And that in the evening, where there is a peak of need, we will use the renewable energy stored in your foundation. Good. So as I said, 5 cubic meters is a very exciting number because it's relatively small compared to the house foundation. Even 33 cubic meters is not so big, considering that that's more or less the foundation volume in the standard housing. Okay, let me go back to multifunctional concrete and now discuss a little bit in detail what it means to have, EC cube foundation in Boston with a photovoltaic power of 10 kilowatt hour on your roofs and has some compare the scenario one where you use photovoltaics plus a lithium-ion battery and scenario two where photovoltaic cells are connected to our EC cube foundation system. And you see the problem. What I was referring to is this peak of demand in the evening after 6 p.m. Where you do not have sun to provide you with the energy. And so his comparison between lithium-ion battery and EC cube led to 35% less greenhouse gas emissions, and that now is quite an exciting number because if you have a house that stores energy in the foundation and compared to the standard lithium-ion battery system saves carbon by 35% per year in 3 years without even considering available solutions. You are hitting the carbon negative concrete because you will compensate with this saving on emissions associated with energy storage, traditional energy storage. You will save the amount of carbon that is associated with making the foundations out of ordinary Portland cement. So that number is really, we believe, extraordinary number because this truly creates that concept of multifunctional concrete as a carbon negative concrete and the concrete that is a part of a solution instead of being a problem. Good. To conclude, ancient Rome experienced architectural evolution through discovery and mastery of concrete. We do believe that today we are on the verge of a new revolution, one that could completely change our perception of concrete and the overall built environment. And we call it multifunctional concrete. And I'm happy to answer questions and use remaining of our time here to discuss this, we believe, revolutionary discovery. Of course, many people to acknowledge at MIT, MIT EC Cube Hub, CS Hub, ILP, and is our industrial partner in some of these developments. Thank you.
All right. Thank you very much, Admir. I thought this was a great presentation. So as we go into the Q&A, I'd like to introduce you to the EC Cube Hub's Executive Director and a research scientist within the Department of Civil and Environmental Engineering. You've seen his name a couple times throughout the slides, Dr. Hissam Azari-Jafari.
Thank you very much, Andrew, for the introduction. And thank you so much, Admir, for showing this multi-year innovations and deployments in very different geographical contexts so far. And we're hoping to expand this opportunity and collaboration to other continents and different contexts as well. I'm going to join you for the Q&A session. There are lots of questions in the chat box, so I'll try to bundle some of them together to make sure that we have enough time to cover all of them. But Admir, I'm going to start with a few aspirational questions about where the idea comes from. It's both genius and counterintuitive when you think about a conductor like carbon black and at the same time concrete as a non-conducting materials. Is there any example in the nature, or
Yeah.
tell us a little bit about
Yeah,
where
yeah.
you get inspired?
So it starts with a little coffee break with the Franz Ulm, where I say like that I would be a jellyfish if I didn't have my bones, because bones are by definition load-bearing structures, materials, but the bones are also very optimized and multifunctional, uh, and they are not optimized for load bearing. They sacrifice a part of this load bearing capacity to accommodate cells that are able to repair constantly bones.
Mhm.
Our entire skeleton is completely regenerated, completely new every 6 years, more or less. Maybe my skeleton, my cells take a little bit longer, considering that I'm a big bone, But every 6 years, our entire bone load-bearing system is repaired, is regenerated. So that is an interesting concept where nature sacrifices a little bit of load bearing, but introduces this self-healing functionality. And our bones are full of gaps, blood cells, vessels, tubuli. All of these are, of course, not load bearing and do not contribute to the load bearing capacity, but they have a functionalities, produce energy, things like that. And the idea was really to think about the new concrete, future of concrete as an bone-like kind of system. And so that's more or less where the idea comes from. A nice coffee with Franz, and we said, yeah, new functionalities are essential. And of course, then you choose which functionality you want to introduce and what the functionalities are important in order to create those avoided emissions, and of course, energy storage. Thinking about this architectural revolution where you plug your cell phone cable into a column in your house that has a heart of EC Cube. I think it's just changing completely our perception of built environment, and of course we do believe that there is a space based on the experimental results to make this happen in the real world.
Excellent. So a lot of coffee chats and a multidisciplinary team of researchers from physics, chemistry, systems.
That's right.
Um, that's amazing. At the beginning of your presentation, you talked about the number of buildings that we need every day,
Yeah.
13,000 buildings. And you mentioned that we are going to face a lot of immigration from rural to urban areas, right? And there's going to be some informal settlements, particularly when you think about emerging economies. How
Mm.
do you see multifunctional concrete solution being used in these areas in general?
Yeah, I mean, of course, what I showed there is a big picture. I mean, big picture is the fact that people like to live in the cities, and that projection from the UN clearly takes into account all these social kind of aspects of our population, and uh, how this will then unfold, it's not clear to me, of course. But for what is clear for me is that if we have an architectural evolution that is somehow, reflecting how Romans made their cities viable, enjoyable, big, uh, through use of concrete, and that's really a clear historical example of how a material empowers society to revolutionize completely the way how people live. And in case of Romans, they made the aqueducts, brought the water into the city. This water then allowed them to have a sewage, have a fresh water drinking, have baths, have things in the city that were impossible even to think. You know, Pantheon with 43 meters in diameter was impossible even to think before they started to put piece by piece concrete into that dome structure. So like that historical evidence of a true revolution uh, gives us some sort of a template to think about EC cube as a revolutionary material that will allow us to have a precast elements for standard construction units in the cities uh, that are not just there to make shelter, but also to store energy. And that I think is transformative because you will start thinking about self-sustained, autarkic, I don't know, little home, big home, whatever that constantly leverages on these cycles of renewable energy and energy storage to do things that are impossible to think about right now. Because if it was possible, would have materialized. So there is a bottleneck, technological bottleneck right now where we cannot build a big solar farm in somewhere in Texas and use it efficiently so that satisfies entire need of the state of Texas or even entire US. We cannot do it because there is a technological bottleneck of storing the energy.
Mhm.
And what I believe through carbon and cement, we might start going through this bottleneck and offering solutions that are right now impossible to think about.
Excellent. Well, maybe a few points that I would add to what Admir very well mentioned. First of all, when this technology sparked at MIT, first thing that our PIs and research team thought about is that concrete is an inexpensive materials and it's being used all around the world because it's inexpensive. Making sure that the materials that we are using to add this functionality to concrete at a reasonable cost, at least same order of magnitude, was one of our objective functions. So the carbon black that is being used, for example, you can see that it's being conventionally used in the tire industry, so it exists all around the world. Similarly, the electrolytes that the team has started looking into, it's available from any petrochemical companies. More importantly, when you think about the developing economies, you will see that modular precast elements are very much prevalent, like concrete masonry blocks. So, because the fundamental knowledge has been fully developed right now, we would be able to translate into the local practices of the construction in these contexts as well. And finally, after a lot of communications with different governmental and non-governmental entities in different countries, we realized that low barrier public assets are probably one of the places to start with when we think about emerging economies, like street lights, community charging benches, market stalls, rather than private homes. So these assets are really communal and easier to maintain or under the control of one single entity. Excellent. Moving on to a few more technical, detailed
Yeah.
question, Admir. Talking about can you explain a little bit about the process of nanocarbon forming a conductive wire network in the bulk volume of concrete?
Yeah, I call it the magic of chemistry. We are still trying to understand. Important breakthrough was this FIB-SEM mapping of the connected network, which imaging, which gave us true, experimental result of something that visual of something that we knew that is happening, and now we are kind of decomposing those data cubes and trying to rewind a process from having a clamped system of carbon that is dominated by water into disconnected network in the liquid state through the start of hydration process and water that is being consumed while cement is hydrating, and how this dynamics then translates into true connected nano network. Could be that nanocarbon black, being hydrophobic, is constrained by water, but when water starts to be consumed, the pores are formed, nanopores are formed, and these pores are systematically being hydrophobic, populated by flux of carbon nanoparticles that are by definition connected because they originate from one single unit. That's one scenario that we are exploring. But of course, there is it's a very complex dynamic system, and it's still work in progress.
Great, thank you. You mentioned a little bit about this in your previous remarks about the previous question, but could you tell us a little bit about the limitations of this technology so far, and how would you like to tackle these limitations?
Yeah, limitations are multiple, of course. I mean, you always have you would always hope to have like a battery energy density in your cement. That's not the case. Limitation is that the energy density is by definition low, because we use carbons, what we use, and we have this carbon that is diluted in the load-bearing concrete, and that's a very important statement. It's load-bearing. It's still we always want to maintain our EC cube as a low-bearing material. I want my bones to still work. Okay, I don't want to have a collapse of these structures over time, and so the energy density is an important downside. It's diluted, but still in the order of what is needed to satisfy the, for example, household need. Of course, if you think about some, high density energy storing solutions like batteries, these two play in completely two different categories. I would never put them in competition. Okay, so that's very important to say. Other aspects of the material are, of course, availability of carbons. Carbon black industry, if we are successful in our promise of using this material all over the world in our infrastructure and construction, the carbon black, please invest in carbon black, okay? Like if we are successful in start introducing these solutions as a viable solutions, the bottleneck, the issue will be availability of high performance, high surface area carbons, and if you look at the current production, we need to scale it up significantly. So that's maybe another downside of the system.
Still a lot of work in progress.
That's right.
Thank you. With regard to the self-heating concrete, how is the voltage applied to the panels? You show that in the schematic figure in one of the slides, but please feel free to.
Yeah, it's like two electrodes in this specific case, or four electrodes. You can decide the distance, and then you have a control unit and define the 12 volts, the 24 volts that are going through the system. And of course, the temperature will be very much related to the distance, conductivity, and the distance of your system. And so we carefully tuned the distance, and we found out that 12 volts is good enough at the temperatures that go below let's say below 0 degrees C. So -5, -3 is example that I showed in the video. It's -3 degrees C. 12 volts worked over some time, whereas 24 volts was kind of instantaneous melting.
Great. Thank you. I sincerely apologize because we are not probably be able to address all the questions and respond to them today, but we will keep them and we will gradually go through the questions. And in the meantime, please feel free to reach out through emails and ask for further clarification or questions. Asking another questions about a separate application, Admir, electromagnetic shielding. Do you think this concrete potentially provide electromagnetic shielding and acting as a kind of a Faraday cage within a house or hospital?
I mean, we haven't done yet prototypes to test all these effects. It is possible to think about it. I wish there is someone pushing forward this with us in terms of funding. So I'm happy to hear from potential funders and supporters of this work, and maybe start building some prototypes in the lab and test shielding.
Great, thank you. Another question: why does hydrophobicity of carbon black matter to the full percolation in the cement matrix?
Yeah, hydrophobicity, of course, is not a necessary characteristic. We know that if you functionalize your carbons, you get a better percolation, but also you get worse maybe conductivity features, and so it depends how it's a very much interplay between carbon black surface nature, super plasticizer, and cement you use.
Excellent. For how long of time can electricity be stored in the concrete
It depends on the thickness of your electrodes. It's really very reliable. The time is supercapacitor kind of thing. If the time to charge is 2 hours, the discharge time is about 2 hours. If the time to charge is 6 hours, discharge time is, if everything is ideal, it will be about that same. So it's a diffusion process. So you tune the time of charging and discharging by tuning the thickness of your electrodes.
There are a few questions about the load-bearing capacity. Have you seen any downsides, or how is it comparable with regular?
You are introducing a weak element. The cells in your bones are not load-bearing, so you have this typical graph of mechanical performance that going down with an increase of carbon black. But there is a sweet spot where you still maintain the functionality, load-bearing functionality, and put enough carbon to add functions like self-heating or energy storing.
Wonderful. Thank you. Another interesting question: can biochar be used in addition to carbon or instead of
That's
carbon?
a great question. There is a lot of interest around that. We are starting exploring biochar. Definitely an interesting additive that might give us good results.
Okay, there are 4 or 5 questions about the price of the concrete. How much
Yeah,
additional cost we would expect?
yeah. So maybe Hassam, you can help me on this one. I do remember, numbers, but go
Sure,
ahead if you don't
sure.
mind.
As I mentioned earlier, the addition of this conductive powder, which is carbon black currently in concrete, will obviously impose or incur an additional cost. But depending on the source of this carbon black, the cost magnitude can be totally different. It can be a few times larger than Portland cement, or it can be as negligible as a byproduct or waste that another industry wants to just get rid of and use it for a meaningful application to avoid landfilling. So it can be generated from chemical processes in petrochemical industry. It can be a byproduct of, for example, methane pyrolysis for turquoise hydrogen production, or it can come from the tire recycling processes as well. So depending on the pathways, we can definitely consider a very wide range of the cost. But again, as I mentioned earlier, our mission and the way MIT thinks about this is that there shouldn't be any significant cost incurred to this very inexpensive, what Admir also calls it, democratic material as well.
That's right. Yeah, I mean, remember that we are always, to maintain the mechanical performance, we always add very small amounts of carbon. So percolation threshold, I told you, is 2.53%. So that means that basically, even if it is expensive, then it's order of magnitude at least lower compared to cement. So we are kind of, for some of these applications like self-heating, we are not concerned about the cost of carbon. Of course, when it comes to energy storage, you need the surface area. So these are more specialized carbons, but still, we believe those industries will develop as we move forward.
Wonderful. Could you tell us a little bit about the question is about the membrane in between layers, but I'm guessing they're referring to the separators between different
Yeah.
electrodes of concrete. Could you tell us what material you used?
I mean, you can use anything. It's the condition is that it's insulating and letting ions go through cellulose. It's paper. You can use literally a paper foil as a separator, but you land on different ones that could be more resistant to agents in your cement. And I mean, there are many solutions.
Another question about the emerging, growing trend about data center construction. How can this be used for data center construction? Can it absorb waste heat or dissipate more heat out from the
Oh,
data
I
center?
see. I mean, for data centers, of course, the amount of energy required is crazy. And even if we envision, like a bulk mega carbon cement supercapacitor will require, huge volumes. The good news is we are not constrained by scale. What I want to say is that we show that if you go from 1 cubic centimeter to 250,000 cubic centimeters, the energy storage is scaling. So why not make a cubic kilometer of EC3? Why not? Maybe that will be a big hole somewhere in the middle of nowhere that will be able to carry significant amounts of energy and store significant amount of energy and become maybe viable solution.
That's wonderful. We are on top of the hours. I'm very sorry for not being able to, again, respond to all the questions. Please feel free to reach out to us. and discuss these questions further. Thank you very much, Professor Masic, for the great presentation and Q&A as well.
Thank
And thanks
you
everyone for
all.
joining us. I'm going to hand this back to Andrew.
All right, thank you much. Thank you very much. Thank you both for the awesome Q&A and to everyone who enabled a really fantastic discussion. So as I mentioned at the beginning, the slides and recording for this will be sent to you, so you have the opportunity to review that. And just doubling down on the recommendation to please engage with us, please have a look at the ECCube Hub website, which is eccube.mit.edu, and also the MIT Concrete Sustainability Hub website, which is cshub.mit.edu. So we would recommend that if you have any questions, you reach out to us at cshub@mit.edu and EC3-leadership at mit.edu. And don't worry, I will send these to you along with the slides. So with that, thanks very much and have a great day.
Thank you.
Thank
Bye-bye.
you.
Thank you. Take care.